Every time you get a medical X-ray, you're actually witnessing this spectacular high-energy collision, a clash of matter and energy that's being controlled with just incredible precision. Behind that simple black and white image is a journey of physics that's both, well, violent and elegant. So let's dive in and trace that incredible journey that makes it all possible.
It all started with wild-looking contraptions just like this one. I mean, when you look at these early X-ray tubes, you can just feel that raw, experimental energy, right? The thrill of a discovery that would, for the first time, let us see inside the human body without making a single cut. The basic principles were there, but wow, has the engineering come a long, long way.
So think about it. You're lying there perfectly still, and you hear that machine whir to life. What is actually going on inside that big machine? What's the secret to creating these invisible rays that can literally pass right through you?
And here it is. This is the fundamental secret, all in one sentence. It's all about energy conversion. We take a stream of these tiny particles, electrons, we get them moving incredibly fast, and then we just slam on the brakes by crashing them into a metal target. That sudden, violent stop forces them to shed all that kinetic energy, and it bursts out in the form of X-rays.
So, our story has to start at the very beginning of that electron stream, at a place called the cathode. This is the negative terminal inside the X-ray tube, and it's basically the nursery where our electrons are born.
At the very heart of the cathode is this, a tiny little coil of tungsten wire we call a filament. And if you're thinking it looks just like the filament in an old-school incandescent light bulb, you're spot on. It works in almost the exact same way. We run a current through it and get it glowing white hot.
Now, as that filament gets hotter and hotter, something really remarkable starts to happen. The heat energy gets so intense that it literally boils electrons right off the surface of the wire. The technical term for this is thermionic emission, and it creates this amazing cloud of free, negatively charged electrons just hanging out, waiting for their next instruction.
So really, it all boils down to a pretty simple process. Step 1, we apply a current to heat up the filament. Step 2, that heat gives the electrons enough energy to break free from the wire. And boom, step 3, you have a cloud of pure negative charge just sitting there, ready to be launched.
But, a big scattered cloud of electrons isn't all that useful. That's where this little guy comes in, the focusing cup. It's a negatively charged cup made of nickel that surrounds the filament, and it acts just like a lens. It uses electrostatic repulsion to gather up all those free-floating electrons and squeeze them into a super narrow focused beam aimed perfectly at their destination.
Okay, so we've created our electron beam, we've focused it, now it needs a target. It goes hurtling across the vacuum inside the tube, heading straight for the positive terminal, which we call the anode. This is the target, the wall that our poor electrons are about to smash into.
And it turns out there are two main types of these targets, or anodes. You've got the stationary anode, which is just a simple, fixed piece of metal, and then you have the rotating anode, which is a much more complex spinning disk. The key difference between them really comes down to power and, most importantly, how they handle heat.
And yeah, this picture just says it all, doesn't it? The stationary tube on the left is so compact and simple, which is perfect for things like mobile X-ray units you might see in a dentist's office. But the rotating anode on the right? Well, that's a much more complex piece of engineering built for the really high-power machines you'll find in a hospital.
So why all that extra complexity? Why make it spin? Well, because when that beam of electrons slams into the anode, it creates an absolutely insane amount of heat. Seriously, managing this heat is the single greatest engineering challenge in designing a modern X-ray tube.
Now get ready for this, because this number is just staggering. The entire process is incredibly inefficient. More than 99% of all the energy we pump into the system, all that work to create and accelerate those electrons, is instantly converted into useless waste heat. Less than 1% becomes the useful X-rays we actually want. It's wild.
Which brings us right back to the big question. If you're generating all that heat and you're trying to hit a tiny target with a tiny beam, why on earth would you make that target a spinning disk rotating thousands of times per minute?
The answer is actually really simple and elegant. It's for survival.
Because if that anode didn't spin, the focused beam of electrons would basically act like a microscopic blowtorch. It would concentrate all of that incredible heat onto one tiny little spot, and it would melt, pit, and completely destroy the target, probably in a fraction of a second.
So by spinning the anode, you're constantly spreading that thermal load over a much larger surface area. Instead of hammering the same spot over and over, the beam is always hitting a fresh, cooler part of the target. This allows the whole anode to withstand way higher power and, of course, last a whole lot longer.
Okay, so we've successfully created a burst of X-rays without melting our machine. That's a good start. But our job isn't done. Now we have to take that raw burst of radiation and shape it into a controlled, useful beam that can actually create a clear diagnostic image. And to do this, engineers use a really clever geometric trick called the line focus principle. Check this out. By angling the surface of the anode, the electron beam can actually hit a large surface area, which is great for spreading out the heat. But, and this is the cool part, from the patient's perspective looking up at the tube, the X-rays appear to be coming from a much smaller, sharper point. This little trick gives us a much higher resolution image. But, there's no free lunch in physics. This clever angle has an unavoidable side effect called the heel effect. Because of that slant, some of the X-rays that are created on the heel side of the target have to travel through more of the anode material to get out, and some of them get absorbed. This makes the beam a little bit weaker on that anode side. This diagram shows it perfectly. See, if the center of the beam has an intensity of, say, 100%, the intensity drops off quite a bit toward the anode side, and it actually increases on the cathode side. So the beam isn't uniform at all.
So why does this even matter? Well, this is where it gets really brilliant. Radiographers actually turn this physics bug into a clinical feature. They will intentionally position the patient so that the stronger cathode side of the X-ray beam passes through the thicker part of the body. This helps create a much more evenly exposed image from top to bottom. It's an amazing practical application of a weird physics quirk.
And finally, this whole incredible assembly, the cathode, the spinning anode, all of it is sealed up inside a protective housing. It's lined with lead to absorb any stray radiation, and it's usually filled with oil to help with both cooling and electrical insulation. It makes sure that this whole powerful process stays safely contained right where it's supposed to be.
So, from a simple hot wire to a high-speed collision and a cleverly shaped beam, the physics behind a simple X-ray is just a remarkable story of controlled power. It really makes you wonder, doesn't it? What other everyday technologies that we take for granted are hiding an incredible journey of physics just beneath the surface?